Here we have a hanging mass, mass A, attached by a massless string over a massless pulley to this sliding mass, mass B, moving along a rough surface. And let's suppose that we've already broken static friction here, so the masses are in motion. If we're given masses A and B, and we're given the coefficient of kinetic friction between mass B and the surface, we would like to then determine their acceleration, which we know will be the same for both masses since they are moving as one, connected as they are by this inextensible string. And we'd also like to find the tension in that string. So let's look here at how to apply our usual strategy to a scenario where we have moving objects on either side of a pulley. Okay, so it starts with the free body diagrams. Here we have them. For mass A, the hanging mass, gravity downwards and that tension pulling upwards on it. Then we follow that string over here and see it's the very same string pulling to the left on B. And if it's a massless string, then we know it will have the same tension at either end. So on mass B here, there's that same tension, Ft, pulling to the left on it. And then here's our kinetic friction on mass B. Note that I've drawn the two tensions in blue here, indicating that I'm thinking of them as an internal force. And that's because I'm thinking ahead and I know that I'm going to put masses A and B into a system together, and that will be an internal force to that system. But we're not quite there yet. We need to think about step 2, where we're actually doing something different this time. With our AAA step, with a pulley, we modify our usual procedure. For a pulley system, we still want to align the axis with the acceleration, but B here is accelerating to the left, and A here is accelerating down. We want the axis to be aligned with both of them, but those directions are different. But they have the same acceleration, so it would be convenient if they were both accelerating in the same direction. So what we'll do is, instead of a usual straight axis, we're going to bend the axis. If this is our x direction up here, we'll say left is the plus x direction for that mass. And we want this one to also be moving in the plus x direction there. We're going to make that x-axis follow the string and take a right turn around the pulley. So we have a single axis through the whole problem. We have bent that axis so both masses are moving in the positive x direction. It's just that up here, positive x means to the left, and down here, positive x means down. Okay. So that'll be handy for us when we come to our next step, defining our systems and thinking about Newton's second law. Okay, we've bent the axis. Now let's put A and B into a system here. We'll enclose them in a box that doesn't really include the pulley itself, and it doesn't include the surface, and it doesn't include the planet Earth. It's just those two masses, A plus B. That will be our system. And now let's look at Newton's second law for that system. Okay. So we want to find the acceleration in the x direction. You know the form of Newton's second law for a system. We need to identify the external forces in the x direction. So here, for A, the x direction is down. And we've got gravity that's coming from the Earth, so that's external. But this tension now, that tension is inside our system here. That tension is an internal force, so we won't include that. So we've got gravity in the plus x direction. And then over on this free body diagram, to the left is the x direction. So tension, that's internal. So the only external force in the x direction on B is that force of kinetic friction right there. And note, that's pointing to the right, which is our negative x direction. So in sum, the external forces in the x direction on our system are this force of gravity in the plus x direction and this friction in the minus x direction. It's actually these two forces competing against each other to accelerate the system. Gravity here is trying to draw the whole system forward, and this friction way back here, that's opposing this force of gravity here. So our sum of forces, sum of external forces in the x direction for our system with our bent axis looks like this. That force of gravity minus that force of friction, then we divide by the total mass of our system. As a quick aside for handling our force of kinetic friction here on B, Let's just briefly look at the sum of the vertical forces here on mass B. Normal force balances gravity, so we can write the normal force as mBg, and our force of friction is mu kb times FNB. So here we've got our expression for our usual expression, or expression for the force of kinetic friction on B. So we're going to substitute this in for FFkb. And making that substitution, this becomes this. We can write that force of gravity like this, and that force of kinetic friction like that. And we see that we have now solved for the acceleration of our system in terms exclusively of the givens. So that was step one of our usual two-step procedure for a system here. We've got the acceleration by using the systems approach. Step two then, to get the internal force, that's this force of friction here, that force of tension that we would now like to find. So let's get that internal force, that force of tension, by using N2L for just one object. So we can pick either A or B. A looks simple because I know gravity here is simple. So let's do Newton's second law just for object A here. So N2L just for A. Now let's be careful about our axis. Our plus X axis is down by our definition here. So on this free body diagram, this force of gravity is in the plus X direction, and this tension, although it's pulling upwards, is in our minus X direction. So we've got force of gravity on A minus that tension on A. That's our net force in our X direction in this case. All right, now just a few lines of algebra to rearrange that to get this tension by itself. You can pause the video and follow along, or check my lines of algebra here for yourself. But rearranging this should get us to here, solved for that force of tension. And at this point, we could substitute in our previous expression for the acceleration. So we've taken our solution from step one and plugged it into step two. So we'd plug that in here and solve for the tension. So if you had numerical values at this point to plug in here, you could then plug in those numerical values here and solve for the tension, and we'd be done. We solved for both of our unknowns. You could take this just a step further, do a little more algebra. If you didn't have numerical values, if you wanted to substitute this whole expression in here, then here's the challenge. Can you sub that in there, rearrange, and prove that that force of tension can be simplified to this expression right here? It might be worthwhile to try to do this because getting the answer into this simplified form actually tells us some interesting things about the system. In particular, it tells us that if we removed either mass from the system, if we cut off mass A, then MA goes to 0, the tension goes to 0. The rope goes slack if you remove mass A. Also, if you removed mass B, if that was 0, the tension would be 0. The rope would also go slack if you removed mass B. So if there were nothing holding mass A back, the rope would be slack. What about if you made the surface that B is moving on frictionless? Well, we can get that answer too. We can make the surface frictionless by taking the coefficient of kinetic friction and setting it to 0. So if we set that to 0, make the surface frictionless, well, 1 plus 0 is still 1, and we would still have a tension. The rope would still be taut even on a frictionless surface.